Do you see my screen?
Yes.
Great. Okay, so I'm actually going to split up my talk into two different topics. The first one is looking at martensitic phase transformations. The second one is a little bit different. I saw such nice talks on recovery or crystallization and grain growth these past couple days. I thought I'd show some new results. So let's start off talking about shape memory alloys and martensitic phase transformations. So martensitic phase transformations, these are the enabling mechanisms in a wide variety of functional material behaviors. Ferromagnetics, ferroelectrics, and in this case, ferroelastic materials all undergo martensitic phase transformations. So shape memory alloys, these are ferroelastic materials, and this is one of their well-known properties, the shape memory effect. This is where you can deform a material like this nickel titanium shape memory alloy paperclip is being deformed, and then it can recover its shape by heating it up. So in this video, it's being dropped into warm water. And this is called shape memory. So again, the enabling mechanism here is martensitic phase transformation. This is a diffusionless first order phase transformation between a high symmetry, high temperature phase, which in metals we call austenite, and a low symmetry, low temperature phase, which we call martensite. So for nickel titanium shape memory alloys, the austenite phase is cubic and it transforms to a monoclinic martensite phase. So this is what the phase transformation looks like. A thermal induced phase transformation looks like under an optical microscope. So here the yellow or the gold, that's the austenite phase, and then the brownish, that's the martensite phase. And so you can see all these phase interfaces, which are interfaces where we have austenite on one side and martensite on the other side. So that's what I'm going to talk about today. The major challenge for martensitic phase transforming materials in general, but especially, or I should say, including shape memory alloys, is something called functional fatigue. And this is where because martensitic phase transformations in many materials are reversible, we want to use them in cyclic applications, but the problem is that the material behavior changes cycle to cycle, and this is called functional fatigue. So functional fatigue in shape memory alloys is understood to originate from dissipation mechanisms at phase interfaces, and so it's related to hysteresis. And this is because for 99.99% of shape memory alloys, the two phases are not what's called kinematically compatible. This means that if I was to sort of force an interface between a perfect crystal of austenite and a perfect crystal of martensite, the atoms wouldn't line up at the interface and you would be left with dislocations, and then this wouldn't be a reversible process. And this is actually the case in trip steels. So in shape memory alloys, what happens is that when the martensite forms, it comes in the form of twins, and this sort of approximates compatibility in an average sense. And you're just left with these small elastic strain fields. And so now there's just a slight misfit at the interface. And so the lattice on either side is just elastically strained a little bit. But this is a dissipation mechanism, and in metals where there's elastic strain or stress, there's also going to inevitably be dislocations. And so these are the dissipation mechanisms that occur at the phase interfaces that are understood to be the contributors to hysteresis and functional fatigue. So this is what we wanted to measure here, these elastic strain fields. They haven't really been looked at experimentally, and definitely not in situ. So in 2018, I took some nickel titanium single crystals to the ESRF, and we measured them using dark field. This was at 20 keV, so we had about 107 nanometer spatial resolution. This is our setup. So here's the sample over here. The sample geometry is in the top right. It's a nickel titanium shape memory alloy single crystal, and it's mounted on the goniometer, and then we put the cryostream close to it so that we could cyclically heat and cool it. And this would then cyclically move it back and forth across that phase transformation. So this is what the initial microstructure looks like. This is mapped by phase fraction or austenite volume. So white is 100% austenite and then black is 0%. And you can see it's in the austenite phase at room temperature, but there are some defects here. We know from postmortem microscopy that there's these inclusions in the material. Crystal growth is very difficult with nickel titanium, and so we inevitably get these nasty oxides and carbides. And then there's this sort of line of defects which we weren't able to isolate, but we think it's either these inclusions or these precipitates that like to form in a row in a series. So we have these material defects in the initial microstructure, but that was actually kind of nice because then we could watch the phase transformation interact with these defects. We're only doing dark field on an austenite reflection here. So we're only measuring the austenite phase. And I'll talk later about why we couldn't measure the martensite in this case. So this video, this is uncorrected, unfiltered data. So it's a little rough, but what we're watching is a video as the material goes back and forth through that phase transformation. So here it's at low temperature, it's in the martensite phase. We don't see any austenite, and then we heat it and the austenite phase comes back as it goes through reverse transformation. And then we cool it again and it'll go back to the martensite phase. So we'll watch the austenite disappearing. So this is what we did. And then we took high resolution dark field measurements at a few different temperature points. So this is the first one at room temperature, and I'm showing phase fraction or austenite volume, elastic lattice strain, and then the mosaicity. So the first thing we saw in the initial microstructure when we looked at these dark field maps is that we had these stress concentrations around these material defects. So around the inclusions, there were higher elastic strains, so we could say higher stresses. And then on this one surface of the sample, we saw these stress concentrations. And that's because I took the sample to the ESRF. We found out it was too thick and I polished it. Actually, I think Phil polished it. So we had a bit of stress concentrations on one side. And then we took dark field measurements at 4 different temperatures where the material was partially transformed to martensite. And the first thing that we noticed is that everywhere where we saw these stress concentrations, that's where the material phase transformed first. And this is why we saw that heterogeneous phase transformation going through the microstructure in that video that I showed. And this is why when we look at a differential scanning calorimetry, a DSC curve, we see that those phase transformations are really spread out over the temperature range. It's because of these material defects that we get in our crystal growth. Another thing that we noticed in, now if you're looking at the third column, the mosaicity maps, is that the material sort of rotated quite a bit during this phase transformation process, but it didn't rotate uniformly. The austenite near the phase interface, we can call this a phase interface now because we have austenite on one side and martensite, which we can't see on the other side. This didn't rotate at all, but the austenite far away from any interfaces was free to rotate in response to the heterogeneous, deformation going on around it. So this was just sort of an interesting observation. We saw it in the reciprocal space maps. We saw this is alpha on the x-axis, beta on the y-axis, and we saw, it's pretty uniform at first, a little bit bimodal, and then it becomes extremely bimodal. And so that's how this bimodal orientation splitting sort of is spatially distributed. And so it's just kind of an interesting observation, and it led us to think, well, maybe these interfaces can be seen as a sort of source of constraint I talked about those strict compatibility relationships between the martensite twins and the austenite. So maybe because it has to satisfy those relationships very closely, then it's not really free to change around those interfaces once they form. But what we were really looking for were these elastic strain fields or stress fields. So if you're looking now at the middle column at elastic strain, the whole sample is thermally contracting, but we see these larger compressive strain fields at all of the austenite-martensite interfaces. And what was really surprising about these results was sort of how far away from the interface they lasted into the material. These twins are likely only tens of nanometers wide each domain, but the strain fields, they spread tens of micrometers away from the phase interface. And so that was really surprising, just how impactful these interfacial stress fields are for the entire material. This led us to develop a micromechanical theory that we could use to predict these stresses. It's in our Actimat paper from, I think, 2019 or 2020. And so this model, we used it to sort of verify that, yes, we can see these strain or stress magnitudes, that they're reasonable, but we couldn't do a one-to-one comparison because the compatibility relationships at the interface and thus our model are different for every twin system. And because we couldn't measure the martensite phase, we couldn't do a one-to-one comparison with our model. And that sort of leads me to the end of this experiment and, just sort of a future work and opportunities kind of thing, which is how do we measure this martensite phase? How do we measure the reflections associated with this monoclinic phase? And this is particularly an issue for thermal induced phase transformation, which is what we were doing in this experiment. And that's because the martensite comes in what's called a self-accommodated structure, which is where it's lots of different twins. It's twins within twins. The twins are very fine. They're hierarchical. They're complicated. For the austenite to monoclinic or cubic to monoclinic phase transformation, there's 12 variants. But depending on which twin system they're a part of, they're slightly rotated. And that leads to 192 different possible monoclinic orientations for a single crystal of austenite. So it would be a lot of grain searching. So what we are looking forward to doing instead is stress-induced transformation, because when we stress-induce the phase transformation, everything is a little bit more constrained, and there's a favorable twin system that's going to form that maximizes the work output. And so when the martensite comes, it's much more organized. The domains tend to be wider. So there's only going to be 2 orientations. And we've seen from HEDM that those orientations are going to be close to the austenite reflections. There's basically the austenite reflection sort of splits into the martensite reflections, like we see with some of like Hughes ferroelectrics results. There's other benefits to looking at stress-induced transformation. It's more relevant to the applications where we use these shape memory alloys. They're always being loaded in some way. And these are really important, these stress fields, and then watching any defects that form as a result of those stress fields. No one has imaged them in situ. And so it's left this big gap in the shape memory alloy community that, again, has relevance to a lot of other material systems, functional materials that undergo martensitic phase transformations. So now I want to talk about a different project. This is annealing, recovery, recrystallization, and grain growth in magnesium alloys. And this is my student Sangwon Lee's work that I'm presenting. So here's the textbook image of these processes, right? we start with some highly deformed state of material. Then we start heating it, we start annealing it. The first thing that happens is these dislocations, they get hot and they move around and they annihilate and they form these cellular subgrain structures. And then at some point they can't move around anymore. They become frustrated. And this is where we get the second thing that happens, which is recrystallization. So this is where theoretically perfect new grains form, nucleate. And then we keep heating. Now we have a fully recrystallized microstructure. And then if we keep heating even more, the third thing happens, which is competitive grain growth of these recrystallized grains. So here's the textbook definition of these things. And like Yuban mentioned yesterday, it's a very common and popular post-processing treatment because you get this wide spectrum of microstructure that you can use to optimize for your application. But this process turns out to be particularly important for magnesium alloys. So magnesium alloys are extremely promising. They're strong. Magnesium is, I think, the 7th most abundant element on Earth. And they're extremely light, lighter than aluminum, about 20% the weight of iron. The problem with magnesium alloys is that when you roll them or something like that, they have very strong texture, and that comes from the HCP lattice structure. The strong texture is bad for a lot of engineering applications. It makes it very anisotropic, it makes it brittle in certain directions, and it makes it very difficult to machine. So we would like to weaken that texture. And it turns out that if you add a little bit of zinc, add a little bit of calcium, and put it through this annealing process, then the recrystallized texture is weaker than the deformed texture. So these processes are important to understand so that we can optimize them. So this is what we wanted to study. And we chose this ZX30 alloy because it has that special composition where we see these textures, these weaker textures form with annealing. The material history, we put it in what's called a Gleeble machine. And this puts it through plane strain compression, which sort of simulates rolling in in a lab setting. And this was done at 350 degrees C. We did 10 passes and with a reduction of thickness of 2.2 or a compressive strain of 2.2. So here's our final sample. It's very, very deformed. And then we took it and we cut some X-ray specimen out of it. So before I tell you about the experiments that we did, I just want to talk a little bit about our thought process behind how we design these experiments. And this is the multiscale problem that a lot of people have been talking about these past couple of days. If we do some sort of higher scale, high length scale characterization like HEDM, then we're left with the questions, well, why is this happening? We see what's happening, but what are the subgrain scale mechanisms at play? Whereas if we do something high resolution like dark field, then we might be left with the questions, well, how does this affect the higher length scales? How does this contribute to the macroscopic behavior? And how do we know if what we're seeing is statistically representative? And that's a big one, I think, that we get a lot from reviewers and review panels. So those were what we were thinking about. And so we took these samples to CHESS and did HEDM, far field and near field, but then we also took them to ID6 and did sort of a hybrid HEDM technique that I'll talk about, plus dark field. And so this was our way of sort of bridging the scales where we have that high level sample wide grain average statistical information. We know what the material is doing macroscopically, but then, as our field of view goes down, our spatial resolution goes up, and then we have these data sets that can connect to each other. So I'm going to talk about 3 of these measurements, and this is, I say mostly, but really it's all raw data. So these are all really new experiments we did a couple months ago or less. And so, but I think if there's any audience I can show raw diffraction data to, it's this one. And the data itself tells a really clear story. So the first, I'm sort of going to move from the higher scale to the lower scale. That's how I organized it. So we're starting out at chess, and we did Farfield HEDM. Here's it's a 2 detector setup. So here's one of the detectors. This was done at 55 keV, 990, so about a meter sample to detector distance, 100 micron beam height, and it's what I call interrupted heating. We didn't have a great temperature calibration, so we decided to heat it, hold it for a couple minutes, cool it, and then check it there at room temperature. So all our measurements are at room temperature. But we heated to somewhere between 300 and 350 degrees C, and the total heating was 1 hour. So I'm just going to zoom in so we can see it a little clearer. So our initial as deformed microstructure consists of 2 kind of different things. We have this powder, these very fine, highly deformed nanocrystalline grains, and then we have these larger 10 to 30 micron grains. And we've verified all this with EBSD as well. So this is our as deformed microstructure, and then I'll show what it looks like as we heated it. So here we see some big changes. We see those recovery, recrystallization, and grain growth processes. We see that powder go away. We see new grains form, grains disappear, and then they start growing a little bit. And we're left with this very nice HEDM pattern. So again, we haven't analyzed, well, we're analyzing it now, but it's not ready to talk about really yet. But we do see all these things, and we can show examples of them in the raw data. So we see these recrystallization events. I'll show it up here. I'll just play the video again. So you see this new grain form right there. And then we also see these grain growth events. So I'll just restart it, and the grain growth is right here. It's going to be this little grain that we see in the initial microstructure. It doesn't get consumed by that recrystallization process. It just recovers and grows. It grows, and actually then it gets smaller as the microstructure gets into that competitive growth process. So this is our high level data set where we have, we can get the texture measurements, but we could also get grain evolution in an grain average sense for many, many grains. We see, again, these recovery or recrystallization and grain growth processes. We get all of these sort of statistical information as a function of grain size, location, and orientation. So we can do some statistical analysis with that. But then we took it to the ESRF to get a little bit more of a high resolution view. Actually, we went to the ESRF and then chess, but it makes more sense if I show it this way. So this is the first kind of measurement that we did on ID6. It's sort of what I'm calling a partial HEDM scan. It's really where we're zoomed into one part of one ring here. And so you can see sort of the curvature of the ring a little bit. Where our field of view here is just eta, 3 degrees in eta. And then we rocked plus or minus 3 degrees in omega. So I'm not really sure whether to call it near field or far field yet, because our sample to detector distance was 59 millimeters. So it's sort of that weird intermediate field region. But this is at 16 keV, and each scan just took a couple minutes, and we used a 150 micron box beam. And so this is what one data set looks like. This is our initial data set of the as deformed condition, rocking plus or minus 3 degrees in omega. By the way, this sort of partial HEDM type measurement, this was largely inspired by Sonia All's work, her PhD work that she did with Henning and Hugh. So it's a fantastic paper if you get a chance. And also, I just want to point out that this is a good ID6 option if you want multi-scale data, but your microstructure, your material's not suitable for something like DCT. Like our material, it's, you know, it's very heavily deformed. The grains that are there are deformed, they're small. So since DCT is similar to HEDM, I'm guessing that the initial microstructure would not have reconstructed well. So this is a good option if you want sort of a zoomed out, zoomed in coupled data set, but you can't use another technique that's available in 96. So this is the initial data set of the as deformed microstructure as summed over all omega frames, summed over the rocking curve. And then this is true in situ heating where we heated it while we were taking measurements. And so you're going to see the ring shift up from thermal expansion, but then you'll also see these recovery, recrystallization, and grain growth processes. So temperatures in the bottom. So here's our shift, and then we see grains disappearing, we see new grains forming, and we see grains growing. So I'll just play it one more time. So we see things sort of shuffling around even before it looks like most of these processes start. And so we know that the grains are mobile from very early on. These subgrains are moving around and rotating. And then we're left with this nice microstructure. So the other thing that this sort of partial HEDM technique is useful for is grain searching. When you're doing dark field, especially if you need to do some in situ work before you pick which grain you're going to do dark field on, so you can't do it ahead of time, this is a nice technique that you're probably, or John's probably doing anyway, so you might as well record the data. And that's what we used it for. We took measurements of the initial microstructure, but then we sort of paused during this in situ heating process to pick out interesting grains to do dark field on. So this is one of those grains. This grain existed in the initial microstructure in the as deformed condition. And contrary to our textbook view of recrystallization, it didn't get consumed by that recrystallization process. It stuck around, it recovered, and then it grew, and then it was still in the microstructure in the fully recrystallized microstructure. So here's, we did projection scans on this grain and layered scans, but I'm only showing the projection. So it starts out kind of a small, highly deformed grain, maybe 15 micron across, but then very quickly it grows into a large crystal with much fewer defects. And I don't have reconstructions yet, but I can show the videos of these scans. So here's one of the mosaicity angles. So you can see start out very small grain, highly deformed. And then here's what the grain sort of turns out to be. And even though it's going through these, in this case, just recovery and grain growth, you can see it's far from perfect. There's this interesting boundary right here in this intermediate step, and then the grain grows past it, but you still see like this remnants of that boundary in that grain left over. And so there's these interesting features, and and we have strain scans as well, and we'll sort of dive into those features. But the other thing too is that this grain became more equiaxed, and we think probably that is what's going on with all the grains. And so that's one of the things we'll look for in those higher scale data sets. Here's another grain, and we chose this grain for contrast because this grain did not exist in the initial microstructure. This is a true recrystallized grain. And even this grain is far from perfect. And actually we chose this grain because it had this interesting sort of subgrain region in it. If you watch the mosaicity movie here, you'll see that in in this corner, the orientation is different. And we saw it even in this HEDM data, and that's why we picked it out actually, which is that this recrystallized grain has a subgrain. There's that subgrain region. It was so obvious that we saw it in the HEDM data as well. So even the recrystallized grains are far from perfect. But this is the mixture that we ended up with in the final microstructure. We had these non-recrystallized grains from the initial microstructure that recovered and grew, and we had these recrystallized grains that, you know, recrystallized and then grew. And this is contrary to the typical picture that you see or you learn about, which is that the final microstructure is this fully recrystallized grain structure where none of the grains existed in the initial microstructure. But rough calculation, we're seeing in both the HEDM data and this sort of partial HEDM data that about 50% of the grains in the final microstructure had existed in the initial microstructure. They just weren't consumed by that recrystallization process. That being said, about 50% of the grains in the initial microstructure were consumed by the recrystallization process. So we have a lot of questions just based on this first look at the data, like what are the differences between recrystallized and non-recrystallized grains in the final microstructure, and what causes certain grains to recover and grow versus be consumed by the recrystallization process. And so this is where those multiscale techniques come in handy. We're going to look for the answer to this question in the dark field measurements. What's going on intragranularly? Is there any difference in strain or mosaicity spread between recrystallized and non-recrystallized grains in the final microstructure when it's going through that growth stage? And then we can look at the HEDM higher scale data to understand this question, looking at the statistics. Is there something in the internal disorder of the initial grains that makes them be consumed or stick around during these processes? Or is it something about the neighborhood? Or is it something about their orientation? So for this, we'll look at that the HEDM data. So those are the two things that I wanted to talk about. The first one was martensitic phase transformations in nickel titanium. We used dark field to observe the interaction between the microstructure and the defects and understand why, or image why the transformation was so heterogeneous. We looked at interesting things about the austenite-martensite interface. We saw some things that suggest that maybe we could see the interface as a source of constraint, which is not usually how we look at the interfaces. And we were able to measure a bit about the interfacial strain fields that we had predicted to exist at these interfaces, but never measured, certainly not in situ. And we were surprised by sort of the distance of these strain fields. And then in the future, we want to try these experiments with in situ loading so that we can image these stress fields, image the austenite and the martensite on both sides of the interface, and watch the live formations of dislocations. And then in the second experiment, I showed recovery, recrystallization, and grain growth in magnesium alloys. I showed this sort of multi-scale approach where we did HEDM, this sort of partial HEDM, and then dark field. And this allows us to sort of zoom in and zoom out of the material and ask questions on a higher length scale, but then look on the lower length scale to answer some of them. By the way, this partial HEDM procedure, it's good for in situ grain searches. It's good if you can't do some other characterization techniques that needs the grain structure to be a little bit cleaner. And again, it's good for understanding the big picture, but also the mechanisms. So this work, the second half was supported by the US DOE under a center called the PRISM Center at the University of Michigan, led by John Allison. And again, that second experiment was the work of my PhD student, Sang-Wan. And I'd like to thank all my collaborators, but especially the ID6 staff, Carsten, John, and Phil. And I'll take any questions.
Thank you, Ashley, for this very inspiring and interesting talk. So are there questions?
I had a quick question. So Ashley, that was a wonderful talk. I particularly enjoyed, well, I enjoyed both sections, but I had a question on your second section. So you showed some really nice work on the grain structures that form, and you had some mosaicity discussions in there. I wonder if you've been able to look at the microstructure that underlies those and dislocation structures?
We've started to look at it. We're having, we have the regular issues, shift correction and stuff like that. So we're not sure what we're seeing yet, but there's definitely dislocations. There's definitely subgrains, and there's definitely the strain and mosaicity variations that you would expect with both of those things. It's they're small, like you wouldn't be able to pick them up with HEDM, certainly not with EBSD, these mosaicity and strain variations. So it's great that we have dark field to measure them, but yeah, we're still looking into it.
Awesome, thank you.
Yubin, please.
Thank you. Yeah, thank you. That's a very nice talk and a very nice work. I also had a question about the second part. I saw this ERSF near field movies. You see some shift. I guess that's due to heating or something. But
Yep.
I seems also noted there's some relatively position shift between the peaks.
Yeah.
Is that real, or is just, I mean, that means the orientation would change during the annealing of a grain or subgrain?
Yeah, it's both. So like the sample was it was rotating a little. And so John did do some corrections to sort of keep it centered to where we had it initially. But you could also see like there are certainly individual movements at a pretty low temperatures, like in the first or second and third measurement that we took. These grains they're rotating, and we know that they're rotating because only certain reflections are moving, not the whole sample. So I'll try to catch one.
Yeah, that means when the grain is recrystallized, when they absorb the dislocation, they change their orientations too?
Yeah, I think so. In the recovery process, the dislocations are annihilating, and maybe there's some average change to the orientation. The grains are rotating a bit, and I think Sonia showed that too in her Actimat paper with Henning and Hugh as well. That these grains are really active, and the subgrains are really active even before you really get into these annealing processes.
Mm-hmm. Yeah, thank you. That's very interesting.
I see Nicholas raising the hand.
Yes, thank you. Thank you, Ashley, for this very interesting talk. Actually, me too, I would follow on the second part of your presentation. It's more related to also what I was doing in my thesis as well. And I have a question. You said that these recent results, which seem very interesting and full of information for the project, I'm interested to ask you, you said that a lot of the recrystallization grains, about 50% or so, did not come from the subgrain structure itself.
Yeah.
So my question is where you think they are originating from, and okay, maybe you can answer that and I can add a comment afterwards.
Yeah, we came up with this hypothesis actually during the beam time, and I brought it to our collaborators at the Prism Center who study these materials all the time and have for years and years, and they think it's a good hypothesis, which is that we do have some dynamic recrystallization during the deformation process, and that's actually, it's something we want to study it on its own, dynamic recrystallization. It's just a little bit tougher. So we started with static, but we think that there's dynamic recrystallization after each of these passes. And, if we have dynamic recrystallization on the first pass, the recrystallized grains are going to get deformed and deformed and deformed, and they'll just be in that powder. But if a grain gets dynamically recrystallized in the last pass, there's nothing after it to then sort of deform that grain. And so we think that these this combination of grains, that we have these highly deformed powdery nanocrystalline grains, but also these larger, still deformed, but larger and a little bit relatively cleaner grains. We think that they're dynamically recrystallized grains from the last or second to last deformation pass. And our hypothesis is that, I don't know, maybe the cleaner of those grains are the ones that are sort of sticking around, and they're basically kind of jumping the gun on those annealing processes where, I don't know, recrystallization, it's not as, there's not as big of an energetic driver for recrystallization in those grains because they're cleaner from being dynamically recrystallized. That's sort of our hypothesis.
Okay. Then the comment I would like to add is that if you are looking at a specific location on the Debye ring, like for example here on the enlarged image, recrystallization can also take place with a large misorientation to the parent grain.
Yeah.
So I'm not very familiar, but that in the ring, that would be a location that perhaps is out of this
That's
field
right.
of image.
Yeah, so in this data, we have the full ring. This is full HEDM data. So if it we see recrystallized somewhere else, we'll get it. But you're right that in that sort of, in this view, in this like partial HEDM view, if we have a grain recrystallized, it could be off frame. And in fact, it's more likely to be off frame because we're only looking at a small area here. So we just have to be careful with what we say about these statistics. We're not going to say this is what's going on in the whole sample and in all of recrystallization, but we do get a bit more high resolution data than with the HEDM. We can see grain shape more. We can see sort of subgrain activity more because our delta omega is smaller. So we just have to be careful sort of about how we stitch those scales because as we go lower length scale, we get higher resolution, smaller field of view, right? But this is why we combined it with the full HEDM. So we could say, well, how does this contribute to the texture? Well, we don't really know because we don't have the whole picture, but we can look at the HEDM data to sort of answer that question. So this is how we're going to combine it. Obviously, it's going to be a challenge, but we're diving into it. Yeah.
Okay, thank you. And the subgrain structure indeed. It's a vast place to study and find tendencies. Thank you.
Okay, I see a question from Mustafa Khan.
Yeah, I have a question. Well, rather than a question, I have a comment/advertisement. So I've been working on an extension of that Sonia's work that you've shown, that partial HEDM. And we believe that if you, in the cost of some scanning times, you can travel your detector, or you can repeat the same scan you did for the full omega range.
Yeah.
And just by patching the frames around the ring, then we believe that we can actually recover a center of mass map of the deformed structure. We're still working on it. But in a few months' time, we may have a workflow that can produce some results. Yeah, that was just a comment, but it was also absolutely great that it's actually even got a use in the in situ experiments.
Yeah, I'm looking forward to it.
It looks like the dream technique, looking heavily deformed material and still being able to resolve subgrains. This looks like a perfect technique. Well, it's 12:35, so maybe I would suggest we close the session for the lunch break, and we meet again at 13:50.